Ted, may I ask you a question?
Of course.
Do you think that I should read this presentation, or should I say it in my own words? That's my own words, but I can make it more colloquial, let's say, reading.
Yeah, I mean it's a very well constructed, as I said in my email. I was worried about that if you put it on the screen, some people will try to read it on the screen, and it's very a lot of words. I have some problems like that. I have a couple of pages myself that have too much text on them.
Oh yes, they have special format.
Yeah.
They have special format for the presentation, text presentation. So that's I don't. So I can say something in my own words. That's because they are my words, but something more colloquial, not reading the whole text.
Yeah, that's probably the best thing to do. Yeah.
So you get up very early today.
Well, no, actually I stayed up. I was working on fine-tuning the thing, and I thought I would get some sleep, but when my wife came to ask me if I had any chance to sleep, I looked at the clock at that point, and I realized it was not worth bothering.
But you don't need any sleeping, I know you. On different occasions,
occasionally.
Very well,
Yeah.
Well, we can start.
Oh, okay.
Yeah, yes, okay. They're editing now, and they will connect it also. Excellent.
What do I need to do to show the video? I need to be given the permission to show it.
Press the button.
Press present. Yeah, it says you are not allowed to share your screen. Well, that's not good. Why can't I share my screen? Who is in charge of controlling whether I can share my screen or not? Also share audio. Yes. Select a tab to share. Window.
Okay. Dear colleagues, dear friends, we can start our special event. Thank you very much, initiative group of this event, Professor Andrzej Rusinski, Professor Ted Kochanski, Dr. Adam Ustinovich. We are very glad to see you, to hear you. It's a pre-final session of our conference, and it's my pleasure to thank once more for this possibility for this event. We are in Greece, we are in Athens, and it is a point which is a city which well known on the world, and I think topic of this special event is very close to ancient culture, ancient history of this point. Now, Professor Nikos Bardis will say a few words for welcome for this session. Where is it?
I come to my computer because it's more.
Now we will come back.
We'll come to you
1 minute.
back. Slava, thank you. I was very surprised about the session. It was so nice to hear, to read such things, and people philosophical way they are thinking for today. For today, because humanity is planning the development of societies in space as our technological development allows it now. And in this undertaking, we must take into account all our experience for the development of our society on the Earth, as the repetition of our mistakes would now be disastrous. Um, Here we propose to rely on Plato's, as I read, ideal state, whose basic characteristics were also adopted by Enlightenment years ago, uh, and as we understand, not with a great success. But we must note that the West culture have offered a lot to humanity, and now we must take the next step to the space, to society space, to the cosmetic space, as we suggest. But let's say what Plato described in his ideal state, and always been written about more than 2,000 years in Politeia, the greatest masterpiece, and completed it with discussion developed in two books after that, The Laws and the Politics. So Platonic ethics is a conditional of Socrates' ethics ideas. Plato tried to build the ideal state according to him in correspondence with the essence of the human soul. But at this point, the role of education in the ideal state and the close relationship that, according to the philosophers, as you are, exist between ethics and politics, and that is very emphasized. Art is well known among the ancient Greeks, but nowadays also, these two concepts are identical. So Plato's moral theory is connected with the soul and the morality. Thus, Plato's moral theory enters into the teaching of self-realization, given that the individuals during his next life gradually achieved his perfection, a kind of direct states, freed from the limitation of space and the time, and of course physical existence and sensory experience. And book and research more than 2,000 years ago, Plato described this case that we are today. And today we have to make the next step to the space. But we don't have to forget all this ethics. I think that the most important is to go back to see our mistakes and to start and make the ideal Plato idea now real, free of time and from the space. So I welcome you in Greece. Next time, I think, I hope, I wish that you'll be here and to discuss all that in the Greek symposium with the great food, grapes, wine, near the sea. And we're very glad. Anyway, Slava is here with us this year. So thank you a lot.
Thank you very much, Nikos, for very interesting words for introduction. And it's my pleasure to invite our colleagues, Andrzej, Ted, and Adam, for your words, your presentation, your video. Thank you. Please. Okay.
Oh, what happened? Where are we? We have Something has happened. I don't know what happened. Something happened there. We lost the connection. It's back. I'm back now. I'm on. Why am I on twice? Seem to be on twice. Well, okay. Well, whatever. Okay. So we are ready to show the video. What? When I tried to connect to show the video window, entire screen. Maybe here. Can people see the screen? Can people see the screen?
No,
Not yet.
No, we cannot see the screen, Ted.
No,
Can you see the screen now?
No, we cannot see the screen.
Yes?
No.
No.
just your video without
Okay.
screen.
All right. So something is wrong. It is not showing the screen window. Share a tab or screen. Chrome tab. No, I don't want a Chrome tab. I need. Okay. Share this screen. It says you are not allowed to share your screen. We have a technical problem.
I think there is a question of control.
It's a question of the browser only.
Please allow Ted to control the session. I think it has to be done from Greece.
Yeah, maybe so.
Yeah.
Yeah.
If you could help us.
It's already done, but I think that the problem in the exact browser.
Adam, is it okay if you send once again a link, the same link
Yes, absolutely.
to Greece? Yeah, maybe we will try that way.
But okay, just
And if not, then maybe you can try. Maybe from Poland it's going to be easier to
no.
make it.
Okay, the same problem because it's not. We are not allowed to present this.
Yeah, I think it's a question of permissions. Yes.
Yeah.
Yeah.
Who is controlling right now?
You
I
are
think
in host.
it's Desert in Athens.
Oh, it says your mic is off. Mic is not off.
Maybe you can try another browser.
Well, let's find out why I have two of these.
It's frequently happening because of the browser.
It's not. This is Chrome. Google should be happy.
Sometimes it's necessary to reload the browser and reconnect.
More options removed from the call. All right.
I propose, because we are wasting time, maybe Adam, you can start with your presentation, and in the meantime, Ted, maybe you can figure out how to show this video, because it's getting late.
Okay. Okay. Yeah. Okay. So maybe I will send later to everybody the link to this video. You can see it. It's okay. Shall I start?
Yes.
Okay.
Yes, please.
So let me say that, especially to Professor, the host of the conference, that I'm very delighted to join this conference, especially in Athens, the cradle of the Western civilization that make possible this space flight and other achievements. A couple of years ago, I asked my friend George Zamka, who was the pilot of the Space Shuttle Endeavour, to take to space the CD with the music of Chopin. Because it was in 2010, it was 200th anniversary of Chopin's birth. At the same time, they delivered the cupola with 7 windows. For the first time, they can watch the panorama of Earth. George Zamka agreed, and he presented this music to his fellows, astronauts, and all of them, they said that it's exactly express the emotions and the feelings that they felt watching the beautiful planet. This gave us the idea with George Zamka to present in 2020 in Mount Vernon. This is historic home of George Washington. We presented the educational program which we called You Are the Future. And I just wanted to present you the trailer of this program, but you will see it later. This is about the future of our civilization, let's say, about the cosmic civilization. Because for the first time now, the humanity will establish permanent bases, first on the Moon, then on Mars. And this joint exploration of space requires close cooperation between nations and civilization. As you remember, famous words of Neil Armstrong, we have come in peace on behalf of all mankind. It's a question if we can repeat this now, coming back to the moon, if we can really on behalf of the all mankind. Still we are divided. Still there's a hate between different groups of people, between different nations. We are not together. We are not coming to space on behalf of all mankind. And that's a problem because, first of all, we have from different civilization and we have different attitude to some ideas which we could not be compared and established. But on the other side, this is a problem that was stressed by Polish writer and philosopher Stanisław Lem. I don't know if you are familiar with this writer. He's very famous. 40 million copies sold all over the world. And 60 years ago, he said that we are condemned to technology. And it's true, there is no way back. This is the only utopian ideas that we can come back to the state of, let's say, innocence, that we can come back to forest and live in harmony with nature. It's too late, just we are condemned to technology. And in the same time, in 1964, he wrote kind of most surprising and prophetic statement that technology is an independent variable of civilization. What does it mean? Does it mean that we are not doing what we desire, but what is the achieved model of civilization expect of us? So we are very proud inventing different technologies, but usually it's not us. Of course, we develop this technology, but we have no control on this. Or our control is not inadequate. I'm talking about, especially about military technologies, which is obvious. But the problem is that we cannot stop the technologies, and even if we take some measures to stop the arms race, it's a problem. We can use only the balance of terror. It is shame for me. This is not for the 21st century that we have to only to have balance of terror The mutual annihilation is a threat that can stop us from making things that can destroy our planet. So when we are going to the moon, we have to remember that we cannot take all those problems and conflicts from Earth to the moon. This will be the nightmare. Will bring this rivalization between the nations and civilization to the next level. So, and who can decide, just how to stop it? Just I think that there is no chance that it will be politics or some authorities. Just I think that scientists and engineers have a say, especially the specialists in this, like Institute of Electrical and Electronics Engineers, IEEE. They have a unique responsibility for the technologies that will be developed on other celestial bodies. Again, I ask the question, we should not, the problem that we should not bring all Earth conflicts into space. And in 1486, Pico della Mirandola, the famous Italian philosopher, writer, poet, he wrote his speech, De Hominis Dignitate, that's mean on the dignity of man. This is considered as a manifesto of humanism, and he was arguing that man is a unique feature, that he has a complete freedom of choice given to him by God. Humans can either return to the animal-like state or evolve to a higher spiritual level. This depends entirely on the will. There is no humanity. There's no need for humanity to be bound to Earth. Just we can, thanks our technology, can move, visit other planets and celestial bodies. There is no limit. Maybe the only mortality, our mortality is a limit, but we also are working on this. But the difference is that this different situation is that on Earth we are living in, let's say, biosphere, this ecosystem, which and on other planets we will be absolutely, completely, entirely depend on technology. Because of the distance from Earth, it must be an autonomous system. And there's a great danger that we will become enslaved by the technosphere that is our creation. And is it possible to escape this trap? And perhaps it's no coincidence that this question is being asked in Athens. This is the city of birthplace of civilization that took humankind into space. And here in 387 BC, Plato founded his academy. Here in Athens, the greatest minds of antiquity pondered on the categories of beauty through goodness, wealth, and health. And we have come back to this tradition and to their achievements, to this heritage. And Felix Konieczny, it's a name of renowned Polish historian and philosopher, and he was studying about less than 100 years ago, in the 19th century. He was studying the old Earth civilization, trying to discover the formula that could describe fundamental guiding principles common to all societies and cultures throughout history. And he called this formula the pentonym of being, the quinquets, consisting of 5 categories that are common to all civilization on Earth. This is goodness, truth, health, well-being, and beauty. The first 2, the goodness and truth, belong to the spiritual realm, and health and well-being to the bodily realm. And the link between the spiritual and material spheres is beauty. And what is a beauty? Another Polish poet, Cyprian, romantic Polish poet, Norwid, he said that the beauty is a shape of love. It's beautiful, beautiful say. And the appearance of beauty is something that we experience both through logical thinking and spiritual encounters. It's present in art and in science. And beauty is something that we don't need to learn, it's just we discover within ourselves. But the beauty is category that is sometimes rejected by scientists. Of course, many scientists and big mathematicians and physicians, they, like even Einstein, discover the beauty. They say that the universe, the reason that they make discoveries is because they want to discover the beauty of the universe. The same with Copernicus. He tried to discover the beauty of the universe, but on the 21st century, we forget it. You know, just we are scientists. As scientists, we forget that the real reason that we study the world is discovering the beauty and the harmony in the universe. And the key is that we have to present it to the next generations, that the education must be based on the beauty. The beauty is something that is different from artificial intelligence. The artificial intelligence will never have the sense of beauty that humans have. And if we will forget this, trying to make autonomous systems on the moon or in Mars, that are, if we'll give the permission to artificial intelligence to decide about the, let's say, the condition and the technosphere, we will be enslaved. We will lost the place that is given us by God, that we are on the first place in is the dignity of man. Only in this, then we will be able to create life-centered technologies. Only when the value of human dignity will be above all. And next 10 years, I think, that will determine the future of the humanity. If we surrender our freedom and transfer responsibility to AI systems and to the technosphere, we'll surrender ourselves and human dignity. And we human, we are the only beings who are endowed with free will. Our knowledge grows like leaves on the tree of wisdom. If we want to pass this, the ideas of beauty and love to other generation, we maybe will create Earth a better place to live. Because this young generation, our kids, they are the future. Thank you. Thank you.
Yeah, thank you. Please continue.
Ted, how you are doing? Ted?
Please switch on.
Microphone on, yes. Okay, people can hear me now?
Yes, we can.
Okay, let's see if we can get this presentation going. Okay, it says share, select a tab. No, I want the entire screen. Okay. I'm sharing my entire screen. Okay. Here's the video.
Okay.
It's now going, maybe. Oh. You seeing the video?
Yes, very nice.
Okay.
Yes.
We
Yes.
start. We see the.
But let's check if the sound is.
I'm not seeing. It's not. There we go. Okay.
The stars have wisdom.
No.
They share the light of ages.
No sound.
The trees are watchers. They record the years and the seasons.
Dad, could you switch on the sound?
The sound is on over here.
this
I don't
for
know
you.
why it's just stopped sharing. Maybe it's not sharing the sound for some reason.
You
No.
are the future.
Well, let's try again with the sound.
Because it's quite important. The music, especially music.
Yeah, of course. Very nice music.
This is the Prelude by Chopin, the Prelude Opus 28, number 7, and it was taken to space by James.
Can you hear the sound now?
Have wisdom.
Yeah.
No sound?
No.
They share the light of ages.
Oh,
The
no
trees,
sound when you share the entire
are
screen.
watchers.
Okay. Well, that's not so good.
they record the years and the seasons.
So
They do this for you.
yeah, it's not. I don't know why it's not doing that.
You
Can't
are the
do anything
future.
with that. No. Well, we can try again to get this.
For the last time, okay, because we are getting late, and I want to have some comments.
Yeah. Well, it's not sharing the sound. So
Okay, so go ahead and do your presentation, please.
stop presenting. Okay, let me present then my presentation.
Okay, I will send you later the links to all of us, all of you, link to this video.
Okay, so presenting my screen. It's maybe it's possible to open in a browser, but you can see my screen now. Okay, so I will present this energy for space civilizations, and I will say to everyone, "Herete." So good morning from. Very early in the morning here in Lexington, Massachusetts. Okay. So the idea of this whole thing is, since we're in Athens, at least virtually, we should think of this in the context of Prometheus. And so we'll have a couple of remarks in that regard. Then we'll talk about applications that energy is used for many things, but these specific things are very key to making a successful space civilization. Propulsion, habitation, communications, computation, control, surveillance and reconnaissance functions, utility functions, local transportation, and mining and manufacturing, and in particular, fuel and other resource extraction that's needed for production for habitation or possibly for propulsion. And I'll give an example of the MOXIE experiment on the Perseverance rover that's currently operated on Mars. Actually, they shut the experiment down, but it worked successfully. We'll use as a paradigm for this the Apollo program. And then we'll talk a little bit about sources, solar, storage and fuel cells, nuclear and fission. These two are different because this one is really radioactive decay, predominantly alpha particle decay, and this one is actual fission. And then we'll talk about fusion. So, with apologies to all the people who know much more about ancient Greek, than I do and such. Prometheus, from the Plato's dialogue Protagoras, he contrasts Prometheus with his dull-witted brother Epimetheus, or the after-thinker, who gave away all the physical attributes to the animals, and there was nothing left for the humans. So Prometheus compensated by taking the fire from the gods and giving it, along with other civilizing arts, to the humans. Excuse me. In the 2nd century AD, or current era, the satirist Wu Chun pointed out that while temples for the major Olympians were to be found everywhere, there were none for Prometheus to be seen except in Athens and Athenian colonies, where Prometheus was worshipped in Athens along with Athena and Hephaestus. According to Pausanias, who was in the 2nd century current era, the altar of Prometheus in the grove of the Academy was the point of origin for a relay torch race, the Lampa de Foria, and it concluded the Panathenaic festival. The race passed through the Keramaikos, or the potter's district, that's where we get the word ceramic from, who regarded Prometheus and Hephaestus as patrons. The race ended by rekindling the sacrificial fire on the altar of Athena on the Acropolis. So we have a couple of examples. This is by a German painter in 19th century. It's actually an extract from a larger painting. And he brings fire to mankind as told by Hesiod. And this is Heracles freeing Prometheus from his imprisonment on the rock that he was placed by Zeus. And this is from the temple of Aphrodite and Aphrodisia in Turkey. So the historical basis, this is one person's version, mine. Fire provides earliest humanity with access to high quality protein, like cooking, and security and comfort, in that you could warm yourself and you could keep wild beasts and stuff away from you. The cooking fires gave rise to the discovery of firing of clay by accident, initially probably, and hence led to pottery. Cooking in pottery led to the discovery of steam, and later fully exploited by Heron. Firing pottery leads to the discovery of smelting metals and forming metals and transforming materials. And all this then fired the idea of studying the materials and transformations and observations and analysis. Science is born. The person who is responsible, generally considered to be responsible for coming up with this beginning of the natural philosophy, is Thales of Miletus, who was a pre-Socratic philosopher in Ionia. And he's credited with saying, "Know thyself," which has been inscribed on the temple of Apollo at Delphi. He broke with the prior use of mythology to explain the world and instead began using natural philosophy, first to have engaged in mathematics, science, and deductive reasoning. He estimated the heights of the pyramids, predicted an eclipse, which Isaac Asimov described as the battle that occurred where the eclipse was viewed as the earliest historical event whose date is absolutely known with precision to the day, and called the prediction the birth of science. He did have some strange ideas. He thought the earth was a flat disk or a mound of land and dirt floating in an expanse of water. He believed that all of nature was based on the existence of water. He also believed that lodestones had souls because iron was attracted to them. And the same he ascribed to amber for its capacity to attract particles of dirt and bits of material because of static electricity. He was followed a couple hundred years later almost by Democritus, who was responsible for formulation of an atomic theory of the universe, where he described the atom, the not cuttable or atom, of being indestructible, unique to the substance. He had some strange ideas too about how those atoms were constructed and such, but he was followed a little bit later by Aristarchus of Samos, who was the first person to propose a heliocentric model, place the sun at the center of the universe. He also estimated the size and distance of the Earth-Moon system. He was off by a little bit on that one. He did reasonably well come up with the ideas how the geometry worked, but he had a problem with estimating the sun being only 18 times size further away than the moon was. Eratosthenes, who was a mathematician and geographer, poet, astronomer, and a music theorist. He also was the chief librarian at the Library of Alexandria. And he calculated the circumference of the Earth to a fairly high degree of precision. He was off by about 50 or 60 kilometers. Heron of Alexandria, as in Heron or Alexandra, he came along a little later. He was the first real successful engineer in the Greco world, often considered the greatest experimenter of antiquity. He built a steam turbine, a wind turbine, and other inventions and discoveries. He's also said to have been a follower of the atomists, or followers of Democritus. And this is his steam turbine, quite a modern concept. This is a sphere of copper, and these are little jets that allow steam to be expelled from the sphere, which is heated from below here. This is from a woodcut from the 19th century in the Knight's American Mechanical Dictionary. So, to the propulsion, habitation, computation, communications, utility function, local transportation, and mining and manufacturing. This is Perseverance. This is a functional version of Perseverance that is in the backyard for JPL, so they can use it to test things that are going to be actually transmitted to the craft on Mars. It's otherwise functionally identical. There's a mock-up of Perseverance, full size, but non-functional, at the Museum of Science in Boston. I see every Saturday when I go over there to do my thing. On Perseverance, in this location right here, is a little box. And if you make a block diagram of the box, it looks like this. It's sort of a reverse fuel cell. It takes air from Mars, which has got CO2 in it, and using a solid oxide electrolysis, it basically extracts oxygen. Oxygen is then expelled from the system. It requires energy to do that, of course, as opposed to the fuel cell, which puts out energy. So MOXIE, which is an acronym for Mars Oxygen In Situ Resource Utilization Experiment, it's on the Perseverance rover. Main purpose of it is to produce oxygen. It weighs on Earth 37 pounds or 17 kilograms, on Mars 14 pounds or 6.4 kilograms. It takes 300 watts and it produces 10 grams per hour of oxygen, which is enough to keep a Chihuahua who is not being excitable, which is probably unlikely for a Chihuahua, alive in a resting state. This obviously would not make enough oxygen to be used for human consumption, let alone to refuel a rocket to get you off Mars in the future. But it's a prototype of the idea. So if we look at the overall Apollo lunar flight, this is a good paradigm for the whole thing. Chemical rocket provided the primary propulsion. That's Apollo 11 taking off. Batteries on board here provided the electrical power needed to operate the Saturn V. The batteries also provided electrical power for the command module when it was disconnected from the service module. For the bulk of the voyage, the service module provided power from fuel cells. And of course, we had the famous explosion of the oxygen tank in the service module for the Apollo 13. The lunar module was powered by batteries, and the lunar transportation was also powered by batteries. Also on the moon was the Apollo Lunar Surface Experimental Package, which is powered by a nuclear decay radioactive thermal generator. Decay of plutonium produced about 70 watts. These batteries, of course, were considerably more capability than that. And manual labor was used for the geological sample extraction and carrying the samples over to the rover or to the lunar module. Now, I included Skylab here as part of the Apollo system, of course, because it was based on the third stage, unused third stage. It was launched by a Saturn V, so it really does fit into the Apollo's story. Of course, there's the lunar module. This is that's Buzz Aldrin removing the early version of the surface experimental package. This is a Apollo 17 liftoff from the moon. It's the only example we have of actual live video from another planet with a takeoff from that planet, or in the case of the moon. So here's Skylab, and this is after some repairs have been made on it. Each one of these panels could produce more than 10 kilowatts, and of course the piece over here is missing. So the Skylab was handicapped from day one, but it did succeed quite well. Problem, of course, was that during each pass around the Earth, there was a period when there was no sun on the Skylab, and so didn't produce any electricity that period of time. So the average power available, after you included all the power that was consumed by the power conditioning and other things, that was about 3 kilowatts per each array element. There's the command module and the service module. When the reentry process began, the service module was ditched, and so then the command module was operating on batteries only. But when it was traveling to the moon and most of the way back, it depended on fuel cells that were located in the service module. This is a diagram showing where the things were located. This is an actual spare from a it was a flight braided unit, but it never flew, Apollo fuel cell. And this is the design and again, flight rated, but never flown fuel cell on the space shuttle. Design is quite similar, not identical. So if we look at the solar panels, which we saw on the Skylab and also, of course, on the space station, get a lot of power if you're at Earth orbit, or if you go to Venus, for instance. With the efficiency of these systems now up in excess of 30% in the best of them, you can get 300 to 500 watts per meter squared. If you go out to Mars, though, it drops off. So at Mars, you're down to probably 150 to maybe up to 200 watts per meter squared. Go to Jupiter, and it falls off like it's falling off a cliff. You're down to somewhere in the vicinity of 15 to 20 watts per meter squared. And then you have the problem of dust, shadows, possibly like what happened to the little lander that accompanied the Rosetta probe. The lander went into a spot on the asteroid, and the comet, I'm sorry, that and it never got any more sunlight, and when its batteries ran out, that was the end of the line. And of course, seasonality on something like Mars or something, or even on the moon for that matter. Storage and fuel cells are fine, but primary cells good for the boost phase, but you can't have them for too long. Storage cells, you need something, of course, to recharge them from something else. And they're good for translating trickle charges to peak output. Fuel cells, the limit is availability, fuel and oxidizer, typically hydrogen and oxygen. Side benefit comes from that is production of water. So what do you do when you're outside of the range where these things are easily available? Well, most of the time we've used nuclear technologies, either radioactive decay, typically plutonium-238 in an oxide form. It can produce 100 watts kind of thing. And it has a problem that plutonium-238 is not very easily available. It's reluctantly produced, very expensive. It'll work for about a decade or so, though in some cases, of course, it's been operating on the Voyagers since the 70s, though the power levels are dropping. The half-life is 87.7 years. So in the case of the Voyagers, they're getting to 1/2 of a half-life. And the alternative, of course, is then you go to a nuclear reactor. You can get heat directly. You can use direct heat thermal to electrical, or you can go via a thermomechanical electrical system like a Brayton cycle or a Stirling cycle or something like that. Typical power outputs are tens of kilowatts or more, and it's good for planetary bases. It could be good for some radar satellites, mostly done by the USSR, and it could power either electronically or thermally provide propulsion. So the alternative then, after you go through all these, is fusion. There's by the way, that's a piece of chunk of plutonium there that's heating itself up because of the fact that alpha decay is occurring inside it. That's glowing because of that. That's what it looked like on the moon for the lunar surface electrical properties experiment. And this is the radio thermal generator on the New Horizons probe that went out to Pluto. This was an early idea of a reactor, nuclear reactor that the then Atomic Energy Commission, now would be the Department of Energy, proposed, and they built prototypes. At least one of these things did go into space. One of these things also had trouble on the takeoff and ended up in the Pacific Ocean. So they did launch them typically from the Vandenberg, so that if there was a problem, that it wouldn't. It would go into the Pacific Ocean. This is NASA's current idea of using nuclear thermal propulsion. And it's an artist's conception. Obviously, there's no actual design at this stage of the game. You can see something like the Orion craft attached to the one end of this thing, and the nozzles are back here. The nuclear reactor is located in this area over here, and these are tanks for the material that's heated by it. So the question is, well, why is fusion worth doing? Well, because of course E equals mc squared gives you a lot of energy for a very small amount of fuel, and this is the reaction that everybody is working on right now. It's deuterium and tritium. It has a downside. I'll get to that in a second about the need for production of tritium. But by comparison to a 1,000 megawatt coal plant, you need 2.7 million tons of coal per year. 1,000 megawatt fusion plant would require 250 kilograms of fuel per year. That's a kind of a big number. There's a lot of available deuterium. There is no available tritium. You have to make your tritium. And there's a little bit produced by decay in the earth and the atmosphere. But if you use seawater as the reference, a gallon of seawater, the deuterium in a gallon of seawater, can produce as much energy as 300 gallons of gasoline. Some of these are not particularly relevant to spacefarings. There not being much wind in most places, some few. You don't have to worry about waste issues, and there are minimal proliferation issues. But we've been at it for 50 years, and we still haven't made it work. And this is sort of a current view of where things stand over the last 50 years. This axis over here is confinement time and density, and this axis over here is the energy of the ions necessary for fusion. Really, you have to be over in this region 10 kilo electron volts, or equivalent to 100 million degrees Kelvin or centigrade or higher. And the optimum is somewhere around here, around 15 kilo electron volts, or a little above that. This is the area where the most recent work with the lasers has done. You heard about that, may have actually crossed that barrier a little bit. Q equals 1 is the point at which you have scientific break even if you make a certain set of definitions. The goal is to get in this range of Q approaching infinity, and that's when you have ignition, and you can use the energy as you see fit. Of course, you're still limited to a few things. If you produce neutrons, 80% of the energy in the DT reaction is neutrons. You also have to capture those neutrons and use them to breed tritium. and then you have heat that you need to convert into electricity. If you have stray neutrons, they're relatively hard to shield. Lead doesn't work particularly well, and it's heavy. Water works okay. The laser technology has one possibility. You could go directly from lasers or inertial confinement of another variety, triggering a small little fusion explosion, and use that as directly for propulsion. That was a concept that was planned to be tested. It never really got to the final stage where they tested it with nuclear or thermonuclear explosions. They tested it with chemical explosions, and it actually does work, but it's obviously not made to work with chemical explosions. So the further example for exotic type fusion, not the DT or DD, is that you can produce reactions, only produce charged particles, and then you can go directly conversion from the motion of those charged particles to electricity, or in principle, you could gate the confinement and then use the high energy charged particles directly for propulsion. The advantage of all these high energy ways of propulsing is you can get from one place to another pretty fast, as opposed to spending a lot of time in the transfer orbits where you're exposed to a lot of cosmic rays and things like that. So a sort of summary of this is the energy for space civilizations. The countdown to space civilization started in ancient Greece with the beginning of natural philosophy, which led to robust scientific inquiry, and then the application of engineering leading to advanced technology. Fusion energy can be viewed as the neo Prometheus, the new Promethean gift, right? And it can be the foundation of a robust space civilization. Just a couple of quick more pictures here. This is Voyager, still working, Voyager 2 and Voyager 1, way out in space, in essentially in interstellar space. This is data from plasma experiment that's been operating well past its lifetime, was designed to operate through the solar system's grand tour of the planets, and it's well past that point now, and it's still operating. This is data that was received a few years ago, and it's past this point now, further out, but it's still producing data. This is where it currently is as of Friday, a week ago. It's radioisotope thermal generator powering it right there. And this thing is, well, that's a Rodin sculpture of the Greek goddess who started off as a mortal, Psyche or Psyche. There's a mission that just launched a day ago, heading. This is a more ancient Greek style version. That's Psyche and her husband there, Eros. Both of these are in the Museum of Fine Arts in Boston now. But get rid of those. That's what the craft artist conception of what the craft should look like just about now. These are roughly the size of tennis courts, and they produce at Earth orbit a reasonably decent amount of power, a couple of kilowatts, but by the time they get out to where the asteroid is located, the power drops rather precipitously down to a few hundred watts. This is what it actually last looked like when you could still see it. It was launched by the Falcon Heavy. This is the Falcon right here, and that's the probe heading off just after a separation. That's what it looked like when it took off. This is the path it takes. Even though it has a ion thruster on it, the thrust from it is very small. It will use a Mars assist, but it still takes, even with the thruster and the Mars assist, it's going to be 3 years after Mars' closest approach, which is 3 years from now, essentially. Well, not quite 3. It'll take another 3 years. And then it'll hang around for a couple of years and do some measurements. These are the instruments: multispectral camera, magnetometer, and a gamma ray and neutron spectrometer. This is very interesting because a lot of these type of things use a source, but the assumption is there's plenty of cosmic rays out there, and they'll bombard the asteroid, and we'll find out what it's made out of from the essentially emissions that are produced as it's bombarded by the cosmic rays. Now, this is the thruster in a vacuum chamber in the laboratory. That's what it looks like. And the artist's conception, that's what it looks like. There's on board this thing, there's one more little bit here. There's a deep space optical communications experiment. Optical communications has been used in the distances out to the moon. And in fact, as was pointed out in another presentation, there was a image that was transmitted back from the moon of Stanislav Lem, who kind of envisioned it, sort of, in that sense. So this is how the system works on the so box hanging out the side of the probe. There are two very large telescopes, one reasonably large and the other one, the Mount Palomar Hale telescope, which are used as a test bed for this thing. So this Table Mountain telescope emits a beam of light. The probe locks onto it, and then it transmits. And it's not connected to the probe for anything other than power. It doesn't know what's going on inside the probe. It's not transmitting any useful data. It's just a technology demonstration. Down here, this is a technology demonstration by itself. This is a superconducting nanowire detector that detects a small number of photons coming back from the probe. Well, thank you very much. Evharisto Pola, Dziękuję bardzo, and I'm not going to try to pronounce the Ukrainian. That's it. Done.
Thank you very much. I have a couple of comments very briefly. Is it okay if I speak?
Yeah, I guess so.
Okay. First of all, I would like to thank Professor Bardis and Professor Harchenko for letting us in and having this wonderful opportunity to present this vision of the future most significant engineering project which we are planning to do. And we apologize for some glitches and for some delays. So thank you very much for that. And I would like to mention that we invited outstanding people from all over the world, and we are happy to have Ray Garboski here, who is our friend and collaborator for many, many years. And as I said, I see this construction of a future space civilization as a biggest engineering project. And we have some components which are already available to us. Let's not forget about the essence of the DESSERT conference, when we are ready not only for having successes, but we are also predicting failures. So, if, like with any engineering project, we have to make sure that something may go wrong. So we are not only qualified as engineers, but we are also qualified as experts in space failures and security and safety. Ray is an outstanding person for many, many reasons. One of them is that he used to be the member of the NASA Department of Defense teamwork, which was essentially given a mission of creating a new space civilization. Unfortunately, President Kennedy was not around and the project was dropped, so we can continue with his experience. Another thing what I wanted to mention about Ray is he has invented the notion of the supreme engineering, which he called wellness engineering. This is something which have been published, which is ready to go. As I said, we have many components to make this idea of space civilization reality and not just an academic discussion. Thank you very much for your attention, and thank you very much once again, Professor Bardis and Professor Harchenko. I appreciate that. Thank you.
Thank you. Thank you very much. Dear colleagues, maybe you would like to add to ask, please, we have not a lot of time, but welcome. Welcome, Artem.
Thank you. Thank you for this really interesting report, and it's really fantastic, and it's necessary to bring these ideas to reality. But it's interesting to mention the possibility of the reaction with helium-3 and in form of H3 and D, in addition to mention DT and DD reaction, because it's most promising source of energy while we're talking about the space, because it's not producing the neutron and other kind of additional radiation, and it's necessary to take into account because it's really most promising source of energy for some space applications. Thank you.
Yeah, that's a very good point. It has one drawback, however, which is that it requires substantially more confinement, density, temperature product than it does the DT or even the DD reaction. And we're just barely getting, with next few years to say we have gotten to this basic limits on the lower side of what it takes to make the DT reaction work. So yeah, p-boron 11 and the helium-3 reactions are promising in the future, but that's not immediate. That's can take some time. People have hypothesized and maybe even proven in some sense that there may be helium-3 available in some places on the moon, for instance, and other places because of bombardment by cosmic rays, and so that might be useful from that standpoint too.
For future at moon, right? Thank you.
Okay, thank you. I see a lot of questions, a lot of maybe comments, but I would like to invite all our participants, but I ask you to be very shortly. Okay? Irina Leroy, welcome.
Hello, it's Irina Leroy speaking. I just want to really thank you to all of you for making this conference, not only this conference happen, but also be able to invite such great speakers. And what I particularly would like to thank you that for your connection between Greece and history to the current technology, because I do believe that many things that we have around us right now, even physically, coming from that patient that was previously, and from this mystery that was in the Greek methodology, that also was spread around the Europe as a part of our culture even nowadays. So just want to really highly appreciate your connection to that part. Thank you very much.
Thank you, Professor Leroy. It was very interesting, your lecture, your participation to our conference, and we wish next time you will be here with us. We have planned it from before some months, so we are welcome to see you again here. Thank you. Thank you very much. Any more questions, please?
Yes, it's dear Ted, thank you very much for very nice history of space technology, and lifetime for space is very important. 3 years, 5 years, 7 and more, and energy system in space is also a lot of scientist activity, a lot of chemical and so on scientists to bring new technology for energy, and this idea developed, and now we use this technology for car, for other process, and space is a root of innovation for future activity with energy, with this application for the world. Thank you very much. It's very, very nice.
Thank you also very much, Professor Lasky. Vladimir, it was great that you are in Greece, in Athens with us this time. Thank you very much also.
Thank you.
And Sergey?
Yeah, thank you. I'd like to bring an angle, maybe not pessimistic, but more like realistic. So speaking about this transition to space or planetary environment-based civilization, we have two empirical impacts, right? First is a well-known Fermi paradox. I'm not going to go into a long discussion, but everybody knows that if the transition to space civilization was reasonably feasible, then we should have observed by now many of those civilizations, or even one civilization spreading over the galaxy, some observable signs of it. So the second perspective here, also empirical, is our relation on our own planet, our relation with water. So at this time, we do not have, given millennia of development, we do not have any submersive underwater civilizations, sustainable, I mean. And we don't even have sustainable, like water-based civilizations, as far as I know. So the question is, maybe we underestimate the challenge of transitioning from planetary to, which is native to our species and to generally to life on Earth, environment to completely hostile and very different environment of space. And the second question is, specifically to the matter of energy here, which was discussed. Sure, energy is very important, but again, in the record, in the aspect of our civilizations, we have now immeasurably more energy than we used to have even a century or 2 centuries back. But how do we use it? It's diversified, it's spread over in uncounted number of ways. Somebody posts a viral video on a YouTube or somewhere, and it may take us, like just loading it and sharing it could take as much energy as a village could have used in a year and some years back. So the question here is, do we have a societal structure? First of all, in addition to, do we have the energy itself? Do we have a societal structure? Do we have a will and ability to focus on these projects to make this civilization not only technically possible, maybe not now, but remotely, but also thriving and self-sustained? Thank you. Maybe Angie or Ted?
Angie?
Your microphone is closed.
Yeah,
my microphone.
Well,
number one, okay, I hear your voices about some doubts and which direction we should be going and where we are heading and so on and so forth. I would say that much. Number one, this is our obligation to come back to the basic question, who we are. What does it mean to be a human? Okay, and there are different definitions explaining what humanity is and where we are going. I think that our obligation is to be curious about the universe and try to explore the universe, to try to understand what we do understand and also try to understand what we do not understand. So that's our obligation, that's our mission on Earth. That's what we are supposed to do, and we will do that. That's number one. Number two, I would say very strongly that our imagination and our ambitions in terms of creating knowledge, wisdom, goodness, beauty, other things like music and sports in space and so on, we can do and think about a lot of things. Let's not be afraid of sort of posing and specifying so-called grand challenge of grand challenges. Let's not be afraid of asking difficult questions. That's what we are supposed to do, not only as humans, but also as scientists, also as engineers. And I would say that much, that personal comment. I was born in Poland, and I had a dream. And everything what I wanted to achieve in my life, I achieved. It's just because I was not afraid of posing different challenges in my life. And I apologize for making those personal comments, but I wanted to let you know that I graduated from the Odessa Polytechnic Institute. I studied in Odessa. Tak что мы можем говорить тоже по-русски, без никаких проблем. I would emphasize once again, let's not be afraid of posing a question of creating the biggest engineering project on Earth. Let's do it. Let's not be afraid. We are qualified. We know what we are doing. We understand a lot of things. Let's not be afraid of it. Sorry for those personal comments.
Thank you.
Now, those are interesting, perspective on things, Andre, because obviously there were examples, not so much in ancient Greece, but more ancient Egypt, where people set off to build pyramids, and some of them succeeded and some of them didn't. They made a start at a pyramid, and one of them has an adjusted angle at the top of it now because of the fact that they came to the realization that it was impossible to build it at the angle they were working on. Another one collapsed completely and ended up being basically a pile of rubble for the most part. And the same thing actually happened in Western, society also, in that some of the earliest of the great Gothic cathedrals didn't make it because of the inability to do the right kind of calculations at the time for the stresses involved in these flying buttresses and things like that. So, yeah, of course, we should aspire to do great things, but we should also be realistic, I think. And I think that's a good point that, I remember what first book I read about space travel, from the era when I was a little kid growing up. Everybody thought about it very easily in a certain sense, even though no one had ever done any space travel at that point. But as we've learned, for instance, the sun is a lot less benign an environment to deal with once you get outside the Earth's atmosphere than we originally thought. The Apollo telescope mount on the Skylab gave us the first exposure to things like coronal mass ejections and things like that. And as we find out more and more about galactic cosmic rays and things like that, we're more and more concerned about these long transfer orbits to go to Mars and come back. And that's one of the reasons why NASA, I think, is pushing for this nuclear thermal propulsion, even though it only cuts a few months off the roughly 3-year timetable that was planned in the earliest, most enthusiastic and less than fully realistic view of going to the moon, which is our backyard, to going to Mars, which is a pretty good haul. And just because we can send probes that made it all the way through the solar system and are now entering interstellar space in some definitions. It doesn't mean we can do that with people unless we have the available energy to drive things faster. And I think that was the first reason why I was interested in fusion, was fusion drives back decades ago. So I think it's a concern. We still need to deal with the issues of living in space. We're still only very neophytes at that. I think we have the record is now somebody spent 1 year in space, not without returning to Earth's gravity.
Okay, thank you.
Thank you. Also, Professor Sokolov want to ask a question, please.
Hello, everybody. Of course, thank you for your presentation, interesting presentation. I have a short question. Many people said about nuclear propulsion system and ion plasma engines, like an electricity propulsion system. How do you think, what technology are closer to be used in the nearest time for space flights? I said not about flights to another stars, another civilization, but for simple research of space. And how do you think what technology are closer? Thank you.
Well, I think the space ion propulsion systems, there's a handful of different ways of doing it, but basically you're throwing stuff that you're throwing it out the back at a much faster velocity than you can with chemical propulsion. On the other hand, typically you're throwing a lot less stuff at any given instant of time, so you're not going to produce the kind of exhaust plume that the Saturn V had. You're producing, and that was basically on the vicinity of a million newtons of thrust, and these other things are millinewtons of thrust. So the differences are 3 times 3, 9 orders of magnitude difference in the thrust that you can get from an ion thrust system. But of course, that's partly due to the fact that they have operated with very low input powers. So you get a small unit that operates at a few hundred watts at most. You can power it from a solar panel, or you can power it from a radio isotope thermal generator. No one has had a chance to really drive a much bigger ion thruster with a nuclear reactor or something like that to find out how successful that would be. There was a test very early on with the ion thrust experiment with a nuclear reactor in orbit that the U.S. performed, but it lasted only for a few minutes. There was problems with the design of the thrust chamber for the ion drive. On the other hand, these low thrust ion systems have operated for, in some cases, the Japanese one that I don't remember the precise name of it, but it's operated for well over a year continuously, and the total operating time in excess, I think, about 3 years, intermittently turned on and off in some cases. So they do work. They require, of course, some fuel, to basically make into the ions that you spit out of the back of the thing. And those tanks of xenon gas, the liquid xenon, and typically what they use on these things, they are occupy quite a bit of volume. If you look at the picture of the Tsiki, that big box is filled to a large extent with this reservoir for the xenon that's used for the ion thrust system, and yet the thrust from it is very, very small. So you really do need this high power process of generating a lot of electricity if you want to do something like that, and then of course you need either an efficient fission reactor or a fusion reactor, preferably. So it's a technology that'll be there, but it's on a growing curve that's much less steep than let's say Moore's law at this stage.
Thank you.
Ray, would you like to say a couple of words? You are an important part of this event, please. Could you say something?
Yeah, where is Ray?
Yeah, I can see him. Ray, can you hear us?
Yes.
Please say something.
Well, I'm really interested in the whole conversation, but I kind of agree with what you're saying. I think we got to face the challenges that are ahead of us, and I think with technology and the knowledge we have, we can certainly face these challenges. But I was interested in the person that said, I've always been surprised there hasn't been more done in our own oceans of putting up cities and stuff. So I was appreciating that one comment. We talked about not even, most of our Earth has water on it, and we're not really necessarily taking advantage of it. And we could learn a lot from, putting up cities underwater as well. So I worry about, and I think this is where I go back to Greece, the philosophy and stuff. I just worry about whether our biggest barrier might be human nature. As we look around the world today, we talk about civilizations in space. How do we avoid some of the things that civilization does now? But I'm excited. I like the presentation. Thank you, Ted, for some of that history and connecting back to Greece. And my wife and I are planning to visit Athens here in the next 18 months. Okay, thank you.
Well, that's a good point, Ray. I think, one of the words that the Greeks gave us is hubris. And I think that's one of our human failings that I don't think we can overcome completely. It'll always be there. And you have examples like that, that ocean Odyssey thing that violated all the rules as far as we know now to go down to look at the Titanic, and, was a major league disaster. So we still have issues we have to deal with. The number of people who've been at the bottom of the ocean is fewer than the number of people who've had their footprints on the moon.
Yeah, if I may, but that's what DESSERT conference is all about. We are talking about security and safety, so we are sensitive not only to successes, but also we are sensitive to potential failures. And I think this is a great asset with this group of people offers to the world and beyond. Thank you.
Yeah, one of the interesting things in bringing up the ocean thing, of course, is space is inhospitable to people if they're unprotected, but structures in space are not too bad an issue because the pressure differential can never be more than 1 atmosphere. Unless you have a hot tank of liquid something or other that boils suddenly and explodes. But for just ordinary habitation, the pressure difference can never be more than 1 atmosphere from one side of the wall to the other. Whereas at the bottom of the ocean, the pressure differential can be 100 atmospheres. And that's harder to deal with in some ways.
So that's all.
Also, Sergey, have a word, something want to additional ask, please, Sergey. Please switch your microphone because we're not listening.
Yeah, that's right. Just a quick comment, completely in line with what Ray and Angie and Ted had to say about the barriers, not only on the technology side, on the technical side, but also on the social, on the human nature side. So that just connecting to what you just said about the conference, Angie, maybe it would be of benefit to bring this social perspective into these discussions also in the scope of the conference. Because definitely there are more challenges here than just with technology if we want to be successful in this project and drive.
We have some plans to organize a conference, thanks to Adam, in Geneva, sponsored by the Organization of United Nations. And before this war in Israel started, we also started talking about a global conference in Jerusalem, commemorating, among other things, Stanisław Lem, and talking about the future of humanity. Because obviously, as much as we understand the role of Greece in our civilization, we also appreciate the role of Israel and ancient Rome forming the foundations of our civilization. So we already have some plans, and maybe Adam, you can comment on them. It will be useful. Thank you.
Yes, I think that first of all, we as engineers and scientists are responsible for the ethical aspect of new technologies. And we have to do all we can to maybe to control the development and explain people not just where we are going. Because some threats are visible, like armaments, that's nuclear weapon, but some threats are invisible, like artificial intelligence, and especially in military use. So, and politics, they don't know nothing about this new technology because it's developed so fast that they are not able to control. It's only scientists or engineers who create those technologies could say something about this threat and not stop it, because it's, as Stanisław Lem said, that it's not possible to stop the development of technology, but to explain people where we are going, just and maybe to educate people, especially young people. Thank you.
Can I have the last question?
Yes, Irina Leroy, please.
I just would like to ask the question that connected to all of you. Before I ask this question, I actually would like to say that indeed, the people who is making the policies and procedures in the political level, directives, as we call it, and I live in Belgium, by the way, in Brussels, they really need to have advices for those people who are working with these technologies. And this glue between the people who is producing these policies and the real engineers like you not exist in many cases. And sometimes it needs to be somebody who is transferred those information from the engineers to the politicians and vice versa, because these communications sometimes are broken or doesn't work, or as you said, the technology is developing so quickly that it's not possible. That's why me as a academic and as a business person who is working in the business and at the same time who's following constantly the political landscapes in terms of their policies, regulations, and other documentary governance documents, basically. I am trying to make myself and I would say I'm trying to have the wide view and broad view of what is going on in this field in order to make sure that I am, when I speak, I'm matching and all of these puzzles together. As I said in my other presentation yesterday, it's multiply or multi-factors that we are having right now. So it's multi-dimension of the problem, or I hope it is not problem yet. I'm sorry, it's maybe a very strong word. But my question to you is following. If as a teacher, as an academic, when you see that your students who graduated or who are still students using your technology or your knowledge or what you teach them in a not right way, what would be your reaction?
Adam, I think you have to answer this question.
Quite difficult question, but again, I just quote the studies of Len. You cannot stop technology. We are not able to stop it. Just we can only make the education of young people better. That means the quality, the idea of beauty as and the human dignity. There must be the basic of the education. Just we cannot only think about how to use and monetize these technologies anyway. Just not counting on the human dignity. That's but it's philosophical. Not only philosophical, but it's a question of our civilization. Maybe it's too late for that. Just maybe not. Just this is a question to you.
Yeah. The other point, another question. Our technology, it's kind of continuation of ourselves or the humans, because we creating that is the way how we want, like how we want they behave, right? And in the relations, and I believe that all of the technologies based on the relation mythology, we also spoke about the different culture, and Greece, one of the best example, Italian culture, again, many cultures, and of course that somebody, it depends on which culture it's contribute in which field, scientific field. But well, if let me get my thoughts all together. So in the human relations, when we have a family, man and woman in the family, in the case if both of them are mature enough, are adults enough, their relations are kind of very healthy, so they could create a good family. The kids would be raised more or less in the right direction with the respect of the nature, for instance. When we give the technology, the same works with the countries. In my opinion, in other period of our human history, when technology appears, we were ready for this technology. Actually, sometimes we were ready before this technology, new technology appears and help us to stimulate our growth. And now we are giving the technology for those who maybe are not ready, who is not mature enough, not having enough understanding how to use those technologies in the right way, and maybe not understanding the danger and pluses and minuses of this technology, how to estimate the maturity and the readiness of the society and different regions in terms of the using those technology and not misuse this technology.
Yeah, I think that we are coming back to this issue of the sense of beauty, that creating technologies, just we sense the beauty of this technology. That means this is kind of harmony. And maybe Ray will say something about this, because it's his word, this wellness engineering. And wellness engineering is a multidisciplinary approach to the technology, that it's not only the effect is in one, is not only energy, not only social things, but all together, just all together. Just this is the different approach, that we are not specialists in the physics or sociology or psychology, but we need something that the science will be more complicated, just take into consideration different approach to it. I think that Ray will say something more about this and more interesting than me.
Yeah. Well, again, when we were talking about the wellness, we were looking at wellness in a holistic way. So we're looking at the spiritual element, not just the physical element, the mental element, the psychological elements and stuff. And so when we're talking about looking at that, the other thing I'd like to introduce quickly is the whole concept of wisdom. And we'll go back to the Greek a little bit, Sophia kind of concept and stuff. And if you look around the world today, you look at all our leaders, I'm not sure you would identify any of them as being wise. And so one of the things I'd like to start bringing back into conversation is that whole issue of wisdom in a holistic way, as well as wellness engineering. So and some of the things we're talking about and some of the barriers that we're going to be talking about in future civilizations are in fact things like religion, are in fact the things like human nature, something like that. If we look at all the wars and different things, they're either tied to some element of greed, territorial or religious in nature and stuff. And so if you think about it in a holistic way, you don't see the barriers that humans have created and things. So when we talk about wellness engineering again, we want to really bring in the spiritual, the ethical, the moral elements of being a well person or a well individual or a well society, which is kind of even more important. So we're just scratching that surface in our discussions, but there have been a couple of papers I've written which discuss some of that. So I'm hoping that explains it, but it's a difficult thing to get across in today's society when we look around the world and how bad civilization is in some ways compared to what it could be if we could just work together.
Yeah, thank you, Professor Ray. And the last question. Recently, I participated in the conference that for industry and space and defense industry and space that I'm also have certain knowledge, not as you, that's why I'm so careful. And we were speaking about the lack of the regulation in the space industry. That a lot of, I would say, the road rules like we have when we are driving the car don't exist. And this is what the big challenge from the ethical part, from the policy part, from the regulations again, part from the law. What is your thoughts about that? Would somebody actually will follow those rules of the space and the ethical behavior there? Do you know about anything like, or maybe in general, if what is your thoughts about the regulations for the space industry?
Well, I think one interesting area of things are that when we talk about space in terms of pieces of stuff, we have a characterize this as probably in the process of putting this talk together. I can't say I read every word of it, but I went through fairly extensively a document called Stages to Saturn, a technological history of the Apollo Saturn launch vehicles. And it's hundreds of pages long. It was published in 1996, looking back at the Apollo launch system. And one of the things that was most fascinating about it was a lot of the technology that ended up in Saturn. Well, it started in Peenemünde in Germany, but when it came to the United States, it was in the hands of the military by and large, and it went into the process of developing ICBMs and things like that, and then it was transitioned to NASA. And so around 1960, it transitioned to NASA. Von Braun came over, and a lot of his team did. But there were also management processes that moved from the Army and the Air Force to NASA. And one of the points that was made in this document that I was reading was there was a very substantial dichotomy between the military view of things and the NASA view of things. NASA wanted everything to be tested to the level of high level of dependability because there were going to be people on board this thing eventually. Whereas the military were launching ICBMs and said, well, if it doesn't work, we can fire another one. You know, whether it's a test or whether it's an actual war, it doesn't matter. Make another one. And so as long as you had enough of those, it didn't really matter if some of them failed. So it turned out that some of the test procedures and things that were developed for these components of the engines and stuff like that had to change radically because of the NASA's view that you didn't want, and in fact you didn't have any failures of the Saturn V itself in all the launches. I think that's the kind of thing that we have to think about in that context. Today, for instance, we're finding stuff in orbit that nobody put up there, but it's pieces of things that went and collided with something else. And now we find fragments, sometimes fairly good-sized pieces of stuff that are floating around, heading to collision course with other things, like space station or various satellites or even human vehicles. And nobody really thought about it when they started doing it.
Dear colleagues, excuse me, but time is over. We need to finalize our conference. Hence, I would like very many thanks for this extremely interesting discussion, extremely interesting event. I have remembered one more Stanislav Lem. He said that civilization is a function of technologies. And I think our civilization will be sustainable and unsafe if this technology if this technology will be safe and secure. Hence, we need find balance between comfort, between and services and our safety and security. People in Ukraine very good understand this issue because we have the war. Hence, but we need to go ahead and make our world, our civilization safe and lucky. Thank you very much one more for your presentation, for your video. Adam, thank you very much, especially for your film. We hope in more. Maybe later we will see you new film and we will discuss with you. Thank you very much. Thank you very much, dear colleagues. And now we can open our closed session. Thank you. Thank you. Okay, let's very shortly finalize our work during these 3 days. We prepared short presentation with the result of our conference. I would like to show this presentation to 1 minute.